Hello everyone and welcome to Pre-Calculus Algebra. I'm going to talk about some things in this video that we may have missed if we weren't in class last Thursday. And the first thing that I want to talk about is something that no doubt you've seen before, but I want to mention it again because we use this all the time. And it's called the Distributive Laws of Multiplication over addition and subtraction. And in short, we usually hear people call them the distributive laws. And what it says is this: if we have something that's multiplied by a sum in parentheses, or if we have something that's multiplied by a difference in parentheses, we can take this multiplier and distribute it to each term of the sum or each term of the difference like this. And we're going to get A times B plus A times C. Distribute the multiplier to both terms of the sum. And if we have a multiplier times the difference of terms, we can distribute the multiplier to each term of the difference. And we'll have A times B minus A times C. It turns out that if the multiplier is on the right-hand side of the product, we can still distribute this multiplier to each term of the sum. And that will give us A times B plus A times C. And if we have the multiplier on the right distributed to a difference in parentheses, we can take this multiplier and distribute it to each term of the difference, giving us A times B minus A times C. Now let's just look at an example or two. Here we have a multiplier, 3, times a sum in parentheses. We can distribute that multiplier to each term of the sum. And we're going to get 3 times x plus 3 times y. Another example, maybe we have a multiplier times a difference. We can distribute that multiplier to each term of the difference. And so we'll have 6 times x minus 6 times 2 So these are some examples of how we can use the distributive law of multiplication over addition and subtraction. Now, there are some things that we might be tempted to do that the distributive law doesn't tell us that we can do. Let's look at cases like this. Here are a couple of things that we might be tempted to do, but there's no mathematical law that tells us that we can do this. Multiplication does not distribute over multiplication. So if we have a multiplier times the product of two things in parentheses, we can't distribute that multiplier to each factor in the parentheses. We can't do this, so to speak, and say, we have A times B. We distributed A to the B. And we have A times C. We distributed the A to the C. We might be tempted to do this, but it doesn't work. And maybe what I should do is leave the equal sign here. Don't do this, it doesn't work. And just to drive it home a little bit farther, we're going to look at an example where it doesn't work, just so that we're convinced that it doesn't work. Now, in addition to trying to distribute multiplication over multiplication like we did here, we might be tempted to distribute multiplication over division. And that doesn't work either. We might be tempted to do this and say, okay, we have A times B and we have A times C. So that's going to give us AB over AC. Again, this is a no-no. It seems to make perfect sense. But if we do this, we're going to come out wrong every time. So multiplication doesn't distribute over multiplication, and it doesn't distribute over addition either. I'm sorry. It doesn't distribute over division either. And I'm mentioning this because, in my calculus classes, every now and then I have some students to try to do this, and of course it doesn't work. And they're just shocked to find out when they get their test back that they don't have the right answer. And in their case, I kind of feel sorry for them because it's not the calculus that they're getting wrong. It's the algebra. And they have this idea that multiplication distributes over a product, or that multiplication distributes over a quotient, and that just doesn't happen. Now let's look at some examples, not using variables A, B, C, but using just whole numbers to convince ourselves that this really doesn't work. Here's a good example to look at, because we can compute this without using the distributive laws, or even trying to use the distributive laws. So we can get the right answer without having to resort to distributive laws or anything like that. We've learned that in algebra, when we see parentheses, they say do me first. Okay. So we'll compute 3 times 6 first, that's 18. So this is 2 times 18, and that's 36. And let's note is that visible? Maybe not. This is correct. So if we try to do this if we try to do this by distributing a multiplier over a product and we get a different answer, we're going to know that we did it wrong. So let's see what happens when I try to distribute this multiplier over the two factors of a product. I have 2 times 3, and I have 2 times 6. 2 times 3, that's 6. 2 times 6, that's 12. Now we know that this is right. 2 times 3 is 6. 2 times 6 is 12. And 6 times 12 is 72. Yep, this thing is incorrect because we know this is the right answer. So where's our mistake? Did we make the mistake here? Is 6 times 12 equal to 72? Yeah, it is. So we didn't make a mistake going from here to here. Did we make a mistake going from here to here? Is 2 times 3 6? Yeah. Is 2 times 6 equal to 12? Yeah. So we didn't make any mistake going from here to here. Our mistake is going from here to here. This is our mistake. We can't do what we just did. We can't do this. We can't take a multiplier and distribute it to each factor of the product. There is no such thing as a distributive law of multiplication over multiplication. Doesn't work. So our problem was we tried to take a multiplier and distribute it to each factor of a product. Doesn't work. So let me summarize this. Okay, in summary, let's note in pictures what we can and what we can't do. If we have a multiplier times the sum of two terms in parentheses, yes, we can distribute that multiplier to each term. A times B, A times C, and we can add them together. If we have a multiplier times the difference of two terms in parentheses, yes, We can multiply the multiplier times each term of the difference and subtract. These we can do. We want to do them whenever the opportunity presents itself. Now, what can't we do? If we have a multiplier times a product in parentheses, can we distribute the multiplier to each factor of the product? AB times AC? Nope, we can't do that. We can't distribute multiplication over multiplication. And what else can't we do? We can't take a multiplier and distribute it to the numerator and denominator of a quotient. So if we have a multiplier times a quotient in parentheses, we can't distribute the multiplier to the numerator and divide it by the multiplier times the denominator. It does not work. Now I've said my piece. Let's look at some examples that we did Friday in class. Here's our first example. Solve for x. And here's our equation. 2x divided by x plus 3 equals negative 6 over x plus 3 minus 2. And remember at the end of the first class we said there's something that we should do when we're solving an equation before we even attempt to solve it. And what we do is we find the restrictions on the variable. X is our variable. Are there any restrictions on what x can be or what x can't be? See, what's the one thing that we can't do in math? The biggest sin in math, we can't divide by 0, right? Well, we're dividing by x plus 3 here. We can't allow x plus 3 to be 0. So x plus 3 can't be 0. And that's the same as saying this. Just move the 3 to the other side. X is not equal to negative 3. So we want to make sure that we're aware of that as we go through the procedure of solving this equation. And now that we've noted what our restrictions are, namely that x can't be equal to negative 3, let's solve. We all hate fractions. So let's multiply both sides by the denominator, x plus 3. Whoops, whoops, whoops. Okay, we divided both sides by x plus 3. And on this side, we have x plus 3 times a product. Now, before we distribute the x plus 3, let's see, when we multiply or divide both sides of a fraction by something, we have to make sure that what? We have the right to multiply or divide both sides of an equation by any non-zero real number. So what we did here is valid as long as x plus 3 is not 0. to do what we just did, we concede that x can't be equal to -3. And that's something that we already knew. On the right side, we have x minus 3 times the difference. The distributive law says that we can distribute this to the first term, and we can distribute it to the second term. So let's do that. So we have x plus 3 times 2x over x plus 3. And on the right, we distribute x plus 3 to this term. So we have x plus 3 times -6 over x plus 3. And we have x plus 3 times -2. So we'll say minus x plus 3 times 2. And this minus sign comes from this. Okay, now let's see. We can cancel as long as x plus 3 is not 0. We can divide top and bottom by 0. And we've conceded that x plus 3 is not 0, so we can do this. And we can cancel here as well. Okay, let me erase the board. After our last set of steps, this is what we have left. 2x equals -6 minus x plus 3 in parentheses times 2. I'm going to use the distributive law again, and I'll distribute this multiplier over the sum of two terms in parentheses. And what do I have? 2 times x is 2x. So we have minus 2x. And 2 times 3 is 6, so we have minus 6. I'll get my x's together. I'll add 2x to each side. And we have -2x plus 2x is 0. And we have, on the left side, 2x plus 2x is 4x. On the right side, -6 minus 6 is -12. Oh, good. We can divide by 4 and solve this equation. Let's see. We divide both sides by 4. I guess I said that, so I better do it. So our solution is x equal -3, or is it? Now, something that we need to do is check our answer. But in this case, I don't even think we're going to get this far, because didn't we agree right at the beginning of this exercise that x could not equal -3? That was our restriction, wasn't it? Our restriction is that x is not equal to -3. If you look at the beginning of the exercise in your notes, you'll see that. And when we solved the problem, we came up with x equal -3 as our solution. It turns out the exercise that we started has no solution. Sometimes that happens. And when we find out that there's no solution, it doesn't mean that we did anything wrong. It doesn't mean we should try a different way of solving the problem. If we have an exercise and there's no solution, then no matter what we do, we're not going to get a solution. But some exercises just don't have solutions. And this was one of them. When it comes to doing applied exercises, there are 6 points that our text emphasizes. First of all, read the exercise carefully, more than once. This is important. An exercise or a problem of any complexity is not going to be something that we can understand completely reading it over once. And with my advanced statistics students, if they're preparing for an actuarial exam, that's for professional statisticians, they have some rough exercises. And I'll work through them with my students, and I'll read the exercise carefully, and I'll say, what? So you know what I do? I read the exercise carefully again. And usually after I read it again, you know what I do? I say, I still don't know what they're talking about. And I'll read the exercise carefully again a few more times. And I still might not know what they're asking for or what they're talking about. So I'll write a few things down that I do understand from the exercise as it's stated, and see if that will give me any more insight. I do this with my students because I want them to understand that any kind of a problem or exercise that's not completely trivial is going to be something that we don't understand the first time we read it. We're going to have to read it, we're going to have to reread it and reread it until we get the sense of what the problem really is. Everybody has to do this. Nobody comes out of the womb knowing how to do applied math problems. It's an acquired skill. And it's not easy for anybody. Well, I'll take that back. For somebody that might be the hybrid offspring of a human being and a space alien, maybe that person's smart enough to read an exercise once and be able to solve it. But for us mere mortal humans, no, it doesn't work that way. We have to read it a number of times to figure out exactly what it is they're talking about, what they're asking us to do. We don't get the sense of it the first time. The second thing that we do, once we've figured out what it is that we're looking for, give whatever it is we're looking for a name. For example, if we're looking for area, call it A. If we're looking for volume, call it V. If we're looking for profit, call it P, and so forth. Just something that will remind us of what that variable represents when we look at it. Here's a side point, because I've noticed that some of the examples in our text, even early on, involve two variables. If we have two variables that are related, express one variable in terms of the other in an equation. So if we have two variables that are related somehow, express them both in an equation that relates the two variables. 3, draw a picture when relevant. So if this is something that has a physical representation, let's say we're looking for area or volume or something like that, we can draw a picture. Finally, solve an equation. This is big. Check our answer. Don't be like I used to be. I used to get an example and go, I'm done. I figured it out. And I never actually went back to see if my answer worked. When we get an answer, let's check it and make sure it works. And this is something else also that I still have a problem with if the exercise is complicated. This seems like a stupid thing to end up saying, but it's not. Sometimes exercises can be complicated enough that when we finish, we forget what it was we were trying to find. And I make that mistake sometimes, so I know that this is a good idea. Make sure that we've answered the original question. Don't just come up with an answer and not realize that in trying to solve the original question, we solved something else instead. So make sure that we've answered the original question. These are the steps that the text tells us to take when we do applied problems. Now let's do an applied problem. We'll do the one that we did in class the other day. Okay, here's one of our exercises. A total of $10,000 is to be divided between Sean and George, with George receiving $3,000 less than Sean. How much will each person receive? Okay, I got some of that. Let's read it again. A total of $10,000 is to be divided between Sean and George, with George receiving $3,000 less than Sean. How much will each person receive? Okay, I'm getting it. We have a total of $10,000, and the entire amount is going to be given to Sean and George collectively. Whatever is not given to Sean is going to be given to George and vice versa. And the amount that George gets is going to be $3,000 less than the amount that Sean gets. And we want to know how much each of them get. Okay, So we want to know how much does Sean get? We want to know how much George gets. So we might as well do it this way. S for Sean, S is the amount that Sean gets. G for George, G is the amount that George gets. And the entire amount, $10,000, is distributed to Sean and George, although not equally. But this tells us that the amount that George gets and the amount that Sean gets add up to $10,000. Okay, so we have the amount that Sean gets plus the amount that George gets equaling $10,000. Now, do they tell us anything else? George receives $3,000 less than Sean. So the amount that George gets is $3,000 less than Sean. So we take what Sean has and subtract $3,000 from it. This is George. The amount that George gets is $3,000 less than Sean. I think that's all the information that we need. Do we need to draw a picture? No, I don't think so. We're not measuring height or distance or area or volume or anything like that. So a picture is not relevant here. And is there anything else maybe that we need to consider? Let me think about this. I guess not. It's time now to solve the equations. Which one? We got two of them. We've got two equations and we've got two variables. So I think this is what I'm going to do. What's G equal to? Sean minus $3,000. So can I take something that's equal to G, Sean minus $3,000, and plug it into this equation? I'm going to take this this expression for G and put it into the first equation. The first equation says S plus G. But what is G? G is S minus $3,000. This is our first equation. S plus G equals $10,000. Here's G. S plus G equals $10,000. And now I guess I can simplify a little bit. I can combine like terms. So that will give me 2S minus $3,000 equals $10,000. And next I'll move this $3,000 to the other side. So I'll add $3,000 to both sides. And I'm going to have to erase some more of the board. We combine these two like terms and we get 0. We combine these two like terms, we get 13,000. And now we can divide both sides by 2. There's our solution, we think. But we have to go back and check it and make sure that it works, right? I have S. Oh, you know what? So far, I haven't made sure that I've solved the original problem or I've answered the original question. The original question asked, how much does each person receive? This tells me how much Sean gets. I haven't said how much George gets. Shame on me. Well, let's see. Didn't we have the equation George equals Sean minus $3,000? Sean gets 6,500. So S Sean at 6,500. Poor George. George only gets $3,500. Sean as we recall, got $6,500. Now here's our solution, or at least we think it is. How much does each person get? George gets 3,500. Sean gets 6,500. Now we've got to make sure that it works. Okay, does that work? Let's take how much George gets and how much Sean gets and plug it in. George is 3,500. Sean is 6,500. And let's see, what does this come out to? Okay, so that much works. This is true. But now there's something else also. And oh my goodness, I'm going to have to read how this was worded. Okay, it said $10,000 is to be divided I think that's how it read. Sean and George. So we have $10,000. Sean's going to get some of it. George is going to get the rest. So in other words, whatever Sean gets plus whatever George gets is equal to $10,000. Is this true? Let's plug in 6,500 for Sean and 3,500 for George. $6,500 plus $3,500 equals $10,000. Check. Okay. We checked our answer. It works. Now we've solved the problem. Okay, everybody. New topic, quadratic equations. Quadratic equation in the variable x is any equation that can be expressed in this form. Ax squared plus bx plus c equals 0. A, b, and c, the coefficients, are real numbers, and a is not 0. Well, what would happen if a were 0? If a is 0, that means that this x squared term isn't here, and we just have x raised to the first power. So if a is not allowed to be 0, then that means that there's always an x squared term in the equation. So a quadratic equation always has an x squared term. Does it always have an x term? No, because there's nothing said here about b not equaling 0. If b equals 0, there's no x term. And if c equals 0, there's no constant term. It could happen that b is equal to 0. It could happen that c is equal to 0. Well, let's just see what happens. If b is equal to 0, then this is what we get. Ax squared plus c equals 0. If c equals 0, then this is what we get. Could both b and c be equal to 0? Yeah, they could. In that case, we'd get ax squared equals 0, and that would mean that x is 0. Not very interesting, but it could happen. Now let's look at some special cases of quadratic equations and how we solve them. And this is the first special case that we'll look at. X squared minus c squared is 0, where c is a constant. And we might recognize that the left-hand side of this equation has a special factorization. This is the difference of perfect squares. And here's how it factors. X plus c, x minus c equals 0. The zero factor property says if we have the product of two factors and we get 0, one of these factors has to be 0. I'm sorry. The zero factor property says if we have the product of two factors and we get 0, one of these two factors has to be equal to 0. By the way, our book calls this the zero product property. So you might be familiar with that expression instead. Now, if this is true, then either x plus c is 0 or x minus c is 0. If x plus c is 0, we can move the c to the other side and get x equals minus c. Or if x minus c is 0, we move the c to the other side and get x equals positive c. And guess what? Those are our two solutions. So let's apply this to a couple of examples. Okay, here's an example. 2x squared minus 72 equals 0. And we might recognize that we have a common factor here. That common factor is 2. So we can divide both sides by 2, or better still, factor out the common factor of 2, and then divide both sides of the equation by 2. We divide both sides of the equation by 2, and we can do that with any non-zero real number. And this is the equation that we have left, and we recognize this as the difference of perfect squares. We recognize that 36 is a perfect square, and so we'll write it like this. X squared minus 6 squared is 0. And we use that special factorization, x plus 6, x minus 6 is 0. And that tells us either x plus 6 is 0 or x minus 6 is 0. If x plus 6 is 0, that means that x equals negative 6. If x minus 6 is 0, that means that x equals plus 6. And that's our solution. Now that was pretty simple. Let's try something that's very similar to the one that we just did, just so that I can prove a point. This is similar to the last exercise, but not exactly like the last exercise. We see we do have a common factor of 2 in both terms, so we can factor out the common factor. And then we can divide both sides by 2. And that leaves us with x squared minus 35 is equal to 0. Well, what do we do now? This isn't the difference of squares, so I can't do it the way I did last time. Or can I? Maybe this is the difference of squares. It's just that 35 isn't what we call a perfect square. But can I rewrite this equation as x squared minus the square root of 35 squared? Can I do that? And this is the difference of squares. So we're going to get x plus square root of 35 times x minus square root of 35. And the zero factor property tells us one of these things has to be 0. So either x plus square root of 35 is equal to 0, or x minus square root of 35 is equal to 0. If the first equation is true, we can subtract square root of 35 from both sides and get x equals negative square root of 35. If the second equation is true, we can add square root of 35 to both equations. and get x equals positive square root of 35. And we have our two solutions to the quadratic equation. I liked this example because it showed that even though this number was not what we call a perfect square, we can still solve the equation using the difference of perfect squares factorization. Now, we could have done this a different way. We could have done the first equation a different way, the first example a different way. Let's see how we could do this one differently. Okay, let's start with the same equation, but we won't use the factorization formula for the difference of squares this time. We'll do it a different way. And what we could do is we can add this number to both sides. And then we can recognize that both sides have a factor of 2. And so we can divide both sides by 2. And that leaves us with x squared equals 35. So far, so good. We're looking for x, the solution, x, so we compute the square root of both sides. And here's where we have the possibility of making a common mistake. My calculus students do this sometimes, and it breaks my heart because they do the example correctly right up to the point where they have something like this and they solve for x and they do that. And they do all the calculus right and then they lose credit because they didn't do the algebra quite right. And here's the mistake. There are actually 2 square roots. See, there are 2 numbers that we can square to get 35, aren't there? We can square the square root of 35 and we can get 35. We can also square negative the square root of 35 and get 35. This equation has 2 roots. This is something we have to watch out for. If we solve an equation of the form x squared equals some positive number, the solution is x equals plus or minus the square root of that number. If we have an equation of this form, x squared equals some positive number, there are 2 solutions to that equation. One of them is going to be positive, the other is going to be negative. So this is the thing that we have to watch out for if we don't use the factorization formula. And you know what? I think that's exactly where we ended up in Thursday's class. So we'll put the lecture to rest here. For those of you that didn't see it, you can watch it and study it. And you'll be up to speed at the beginning of class tomorrow on Tuesday. And I will make every effort to be there at 10:30. I apologize for not being there at 10:30.